center on the section part 1 of 3.4 3.5 from our textbook, finding the zeros of polynomial function. We'll do a little bit of graphing break just for the time being, but everything we do here is going to translate itself into graphs pretty quickly as we keep moving through this section. In any case, recall a polynomial function of degree n takes the form f of x. Well, you notice you got all the powers of x going from power n because it's an nth degree polynomial all the way down to x to the 0 power with a bunch of coefficients for each term. We've already talked about this. And all these values are essentially what we'll call real numbers. And one other thing to note is we're going to come into the stage where we're going to find real roots and complex roots. What I'd like you to remember is a complex number looks of the form a plus b times I, where a and b are both real numbers and I is the imaginary number, equivalent to, if we recall, the square root of -1. And one other thing to note is, in all honesty, every real number is actually a complex number. It just happens to have what? A non-imaginary part. B is equal to 0. So the number 4 could be written as 4 plus 0 to the 0i. But we don't really do that. But just make note, all numbers that we have here are complex numbers. Factoring, we talked about this. Linear factorization is bringing everything down. This is the factored form of a polynomial, where we have our polynomial p of x is written as some type of constant, that's some type of real number, multiplied by a series of individual factors. Each of these factors are linear. How come? Because they're first degree factors. They only have x to the first power in them. And all these values, c1, c2, cn, they all serve as what are called roots of the polynomial. So every factor of a polynomial has a corresponding root, or 0, an x value that causes the function to be equal, or makes the factor equal to 0, which in turn makes the function equal to 0. By the way, if the root is real, it's going to be something that we can actually physically graph on the polynomial as an x-intercept. And that's what we've been doing so far in this unit. Every root that we found has been just a standard real root. Lots of them have been at integer values, by the way. And so it's real easy to go ahead and dot them as we're building the graph. They all serve as x-intercepts. One other thing, just a quick remember, some of these roots that you see up here could repeat themselves, and that's the concept of multiplicity. So if x minus c occurs as a factor of the polynomial m times, then c is a 0 with a multiplicity of m. And we've talked about, we'll look at it one more time, but we know what the behavior of roots are based on their multiplicity in terms of how we draw the graph. So in any case, here's the question for this unit. How do we take a standard form polynomial, break it down into factored form so we can find its roots? Well, there's a bunch of ways. We're going to work through a bunch of them today. One of the first ones, so most of what we're going to do here is just factor things. We'll find some roots. We aren't going to graph it this time. But in some of the examples, you're actually going to see a graph that's out there. So here's our first problem that was done for us. We have 2x to the 4th minus x cubed minus x squared. Now the graph isn't perfect, but if you put this into your calculator, you'd see there's actually 3 x-intercepts here. There happens to be a u-turn at the origin. But let's work our way through it just by factoring. Technique 1, look for all your terms. See if you can pull out a greatest common factor. And in this example, we could pull out x squared. And what we would be left with? 2x squared minus x minus 1. Now, can we break down 2x squared minus x minus 1? We want to, because remember, we want to get linear factors. Well, what do we know we could do with this? Well, we look for two numbers that when multiplied give us -2 and when added together give us -1. We can use our composition. So take a look. We'll have 2x squared minus 2x plus x minus 1. That's what decomposition would have us do with this type of problem. Let's keep working with what's inside. This becomes 2x. I'll do something like this. 2x times x minus 1 plus 1 times x minus 1. What do we wind up with? X squared, 2x plus 1, x minus 1. And now we factored this thing wholeheartedly, and we're in very good shape with it. We could find all the zeros. We got an x equals 0 root with a multiplicity of 2. We have a root at x equals negative 1/2 with a multiplicity of 1. We have a root at x equals 1 with a multiplicity of 1. And by the way, you see that now. That again, you'd have to go to your calculator maybe to see it a little bit better, but you can find all those roots clean right out here. Right, second problem, x cubed plus 2x squared plus x. Again, hey, first things first, try to pull out a common factor. Well, best I can do is x. X squared plus 2x plus 1 is what should be left. And I can certainly factor that x squared plus 2x plus 1 is nothing more than x plus 1, x plus 1. And so my factored form would look like that. And in turn, if I want to just kind of write it in a little prettier fashion, x times x plus 1 squared. Where are my roots? At x equals 0, at x equal negative 1, multiplicity of 1, multiplicity of 2. So I kind of know, hey, exactly how I could draw this graph. I know I'd be making a plow through at the root on the origin at 0, 0. My root at negative 1, 0, I'm going to be doing a U-turn. And that's just what we were talking about here. Again, as you work through these problems, just remember what your multiplicity does. Plow throughs, either keep going down, keep going up. Even, make a U-turn. Odd, do the traffic circle type of behavior. If you're increasing, keep increasing, slow down as you hit the root, and then pick up speed as you come out. If you're decreasing, change your speed, get a little bit slower, and then you keep going down and through the root. So there's factoring by greatest common factor. Let's keep plugging. Sometimes we'll have some more detailed polynomials, but grouping might work, just like we saw in decomposition. So if you wind up with something with 4 terms, take a look at them in pairs, see if maybe there's a common factor that exists in both of them that you can pull out. So I'm going to do that on this. X cubed plus 5x squared. As I stare this down, what can I see? Well, I could take out an x squared and be left with a x plus 5. Minus 4x minus 20, I could take out a negative 4 and be left with an x plus 5. Great. X squared minus 4, x plus 5. And if I wanted to, hey, again, try to break it down as far as you can. X minus 2, x plus 2. That happens to be a good old difference of 2 squares. I found 3 roots. That sounds good. A root at x equals 2, multiplicity of 1. A root at x equals negative 2, a multiplicity of 1. A root at x equals negative 5, and a multiplicity of 1. So I have a lot of what I need, again, to draw the behavior. This is an odd degree function with a positive leading coefficient. That's going to be a down, up. I have everything that I really need to draw this graph. I also can, by the way, find a y-intercept. So not only do I have a whole bunch of x-intercepts found, because I found the roots, but gee whiz, I also know that the point 0, negative 20 is also out there on this. How did I find the y-intercept? Simply set x equal to 0. When I do so, the function evaluates to negative 20. Okay. When you see something of this nature, bring everything over to one side. X cubed minus 3x squared minus 4x plus 12. Let's go ahead and take a look at what comes out. Grouping again. Hey, I can take an x squared out of my first batch and be left with x minus 3. On my second, I can take out a negative 4 and be left with x plus 3. Well, kind of close to what I had on that last problem I just did. Got an x squared minus 4, x minus 2, x plus 2, x plus 3. I again have 3 roots. A root at x equals 2, a root at x equals negative 2, a root at x equals negative 3, all with multiplicity of 1. Whoops, sorry, just let me move that up so you can see everything. X cubed minus 3x squared minus 4x plus 12. Third degree polynomial, odd degree, positive leading coefficient. Again, I kind of have a down, up. When I look at this polynomial, I know that if I set everything on the one side, I have x cubed minus 3x squared minus 4x plus 12. When x equals 0, I have a y-intercept at 0, 12. I have one more point that I can add onto my graph to go along with the roots and the end behavior. All right, let's continue. Now, sometimes what we'll have to do is a little bit more complicated. Give me 1 second here, just as I move a few pieces of paper, excuse me. So, now I have a trinomial, but it's at a relatively high degree. This is a little bit more challenging. But this is a technique you used in Algebra 2 before. When you see a trinomial where the powers tend to fall in kind of an even progression, 4, 2, 0, you can use a substitution. You did this last year. You say, hey, let u equal x squared. And what's that mean? U squared is the same as x to the 4th. And so with that substitution, I can change this. X fourth becomes u squared, minus 10x squared becomes minus 10u, and plus 24 is nothing more than good old 24. How can I work this problem now? Well, I can factor u squared minus 10u plus 24. It's u minus 6, u minus 6, u minus 4. Please excuse me. Fix that. U minus 4. U minus 6, u minus 4. And I can solve these. I'd have u equals 6, u equals 4, which is wonderful. However, I'm doing this graph in terms of x, which tells me that what? X squared is equal to 6. X squared is equal to 4. To find my roots, take the square root of x each side. X equals plus or minus the square root of 6. Very important. Remember your plus and minuses here. Don't just say x equal the square root of 6. X squared equals 4. Solutions are x equal plus or minus 2. Hey, how many roots do I see? I see 4 roots at negative square root of 6, at negative 2, at positive 2, at positive square root of 6. Each of them with multiplicity of 1. And look at my graph. You can see, and you can put this in your calculator if you want to, some of the graph, just the upper part, got clipped off just because there wasn't enough space to capture all this, but this function goes up and makes a U-turn at some point in time. But what do you notice? 1, 2, 3, 4 roots, all of them with multiplicity of 1. You also notice we have a what? An even degree polynomial, positive leading coefficient. This is a up. And by the way, that little tippy point where I made my U-turn, it actually is 0, 24. Right, moving on. 2x to the 4th minus x squared minus 3. Same concept. Let's let u equal x squared. So I'm going to have 2u squared minus u minus 3 equal 0. All right, what can I do? Two numbers that are equal to 2 times negative 3, negative 6, and add to negative 1. The numbers that can do that trick are negative 3 and positive 2. So what am I going to look like? 2u squared minus 3u plus 2u minus 3. What can I take out? Well, I can take out a u and have 2u minus 3 plus, hey, 1 times 2u minus 3. U plus 1, 2u minus 3 equal 0. If I want, u equal negative 1, u equals 3/2. Great to know what u is, but this problem, remember, it's cast in terms of x. So over here I have x squared equals negative 1, x squared equals 3/2. Now, x squared is the square root of x must equal plus or minus the square root of negative 1 plus or minus I. X squared equals 3/2 gives me x equals plus or minus the square root of, don't lose your plus or minus, 3/2. And it's very interesting. Take a look at the graph over here. How many x-intercepts do you see? You only see 2 of them. And why is that the case? Because in this problem, we only had 2 real roots. We have 2 imaginary roots. You can only graph real numbers on a graph. We can't graph complex numbers. What's that tell us? Well, exactly what the graph is doing. I can only see 2 roots because those are the only 2 roots that I happen to see. This is, by the way, the square root of 1.5, so a little bit more than 1 Little less than -1 is where those two roots happen to be. That's what the square root of 3/2 would come close to when we approximate. But it's a very interesting concept here. So remember, when your zeros aren't real, you won't be able to see them on the graph. You're only going to be able to see them when you have a real root. Imaginary roots you can't see when you graph. Real roots you definitely will be able to see. The important point though, all of these are true roots of this polynomial. I know some of them are imaginaries, but they still are considered roots of this polynomial. Keep that in mind as we work through these. So we'll take a break with this part of the video and then we'll finish up our second part on a side video.